Hey, welcome back. A little pause there. We'll splice this together, but the battery on my transmitter wore out here, so we kind of paused there and put in a new battery. Okay, so where was I? What I was doing is I had just gotten ready to draw this 5.5 volt equipotential. So 5.5 volt equipotential, and I'll just kind of freehand it right there. All right. This probably deserves another one in here, a little tighter, maybe right in between those ones. I'll just clamp it down right there and call that. Oh, you know what? If I move it just a little bit, it'll be 7.5. Good. So let's find that equipotential. 7.5. And so there's a 7.5, 7.5. 7.5, 7.5. Let me go the other way. Here is a, oops, wrong way. Right there, 7.5, 7.5, 7.5. A little closer. Let me see if I can angle it. Something's bumping me underneath. Good. There. 7.5. Maybe one more, I think. Maybe I'll angle it a little more here. 7.5. Okay, good. And so this one tends to have this arcing around it at a equipotential of 7.5 volts. All right, so that seems like I can start drawing perpendicular, perpendicular, perpendicular. Good. Let's try two more equipotentials on this side. Maybe right clamp. Maybe right here would be good. That says 2.5. So 2.5. 2.5. 2.5. 2.5. 2.5. Interesting. Looks like these are already straight. My guess would they weren't quite straight till they'd get over here, and this one still would have a little bit of arc to it, but it is pretty straight. All right, let's come over here. 2.5. 2.5. 2.5. 2.5, and maybe one more, 2.5. Okay, and so here is the equipotential, pretty straight, of 2.5 volts. And to ramp this third drawing up, why don't I find the potential right there? Looks like 1.1 volts, okay? And so I will do a 1.1, 1.1, 1.1, 1.1, 1.1, 1.1, 1.1, 1.1, 1.1, and 1.1. Okay, so connecting these dots, there is a 1.1 equipotential. And like I said on the other two, let me not draw any more on this. I'm going to scan this and send it to you. But to kind of help you in here, if I put this up here, and let me redo my drawing here. In fact, maybe I'll just, what do I do with the black one? And so I've got the plates on this side, negative, 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 negative. And on this side, I've got the charged ball. This, of course, has an equipotential of 10 volts. This has 0 volts. And it looks like my equipotential, the one that is wrapped up really kind of tight here at 7.5 volts. Another one that's curved but not as tightly was the 5.5 volts. Then interesting, like I said, got really pretty straight, straighter than I thought it would have, was the 3.8 volt equipotential. And then the other ones came out pretty straight also, which makes sense once one of them is straight. That doesn't surprise me. I just would have expected maybe this one to be the first straight one. But there's 1.1 volts and 2.5 volts. And so what you're going to be asked to do is make your drawing. And again, hopefully the lesson you got out here is it's perpendicular and it goes from positive to negative. So down the middle, it would be perpendicular, 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 and perpendicular. Yay! All right, so there would be the electric field pointing from positive to negative. And you begin to see perpendicular, 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 perpendicular. Perpendicular, 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 perpendicular. And perpendicular, 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 perpendicular. And perpendicular, 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 perpendicular. And so, like I said, if you kind of look at this, you begin to see the hybrid between this and this. Because we know that no matter what shape we have, close to the plate, they got to look like this. And we also know no matter what shape we have, close to a sphere, they got to look like that. And so they got to morph from one to another. And so it's morphing, if you will, from radially outward near the point to perpendicular to the plate, and that's kind of what that morphing is. And so that kind of having that intuition helps you kind of look at the patterns we're going to see throughout the semester and what the electric field and the equipotentials should look like. Now let me just check real quick. I don't think there's any discussion questions. Procedures. Oh, yes, there are here. So the first one here says, do the drawings. Okay, so that's what we just did. If you're looking on page 8, it says, do these drawings. They list, I'm not sure why he has 4 here. Oh, I see, because the procedures say, draw any of the 3 of the patterns we have. All right, so if you were here in class, you could pick which ones you want, but I picked them for you. So those were the 3 we did. But then question 2, briefly explain why the electric field is always orthogonal, that is perpendicular to the equipotential line. So I think I answered that quite a bit. And then 3, briefly explain why this particular apparatus can't be used to determine the electric field inside an insulator. Oh, let me answer that one because I did not do an insulator. The 3 I picked didn't have an insulator in them. And so let me say both ways. Number 1, you could just ignore step 3. We didn't do the insulator. But I'm going to answer it for you because I know a number of you would be curious. Had we done the other option, there's this one here, which is a dipole, and then stuck between the dipole is the conductor and the insulator. And they want you to see something if you had hooked this one up, and that is this one morphs the electric field so that it always hits it perpendicular. That's kind of neat to see. And then this one, the electric field goes right through it, and there's actually an electric field inside of the insulator. And so that's one of the lessons, if you didn't get, I'll say it now, we can have an electric field inside an insulator, but you can't inside the conductor. And so the conductor has no field and must be perpendicular to its surface, where this doesn't have to be perpendicular to the surface and can go right through it. And so sure enough, it does. Sadly, though, this is never a really good one. This confuses students when they're here because our equipment cannot measure the equipotentials inside an insulator, because the way our machine works is when you touch it, it actually sucks an electron off and measures its energy. So it only works when it can be a conductor. So if I were to touch it here, it works. If I touch it here, this is a little graphite plate, and it works. And graphite is a semiconductor. But when you touch it here, you get a big fat zero, and that confuses students when they're in the lab. And so I got to spend a little time explaining. And so maybe it's good I didn't try to do this one, and also maybe it's good to say, look, don't worry about question number 3, but for those of you a little bit interested, if you were to hook this up and take it, your machine would say 0, but that doesn't mean the equipotential is 0, it just means this machine can't read it. It can't read it because it sucks electrons off, and an insulator, they can't flow off, so you get a false reading, if you will. So that being said, I think that's it, and I'll call this a wrap, and this is number 3. I better stop counting because I'll lose count here. But this is the, I don't even know the title. What is it? Equipotentials and electric fields or something like that. Or I guess just electric fields from the equipotentials. All right. See you again later.